Hello everyone, Dr. Shane here, and this is the pre-lab video for our first face-to-face activity for the semester. I'm not going to go through everything here. The first thing we're going to do when you come to lab is to come in and check you into a specific lab drawer. Now, if you've had chemistry with us before, this is the exact same procedure that we did. And I have a video from the first semester Gen Chem that talks about how things are going to be set up. So we'll inventory your lab drawers, we'll go over safety, and hopefully we'll be able to do that pretty quickly. We only have an hour and a half. Remember, you're in 2 different shifts, unless you have a really small lab section. So you'll be coming in for an hour and a half, getting your data, taking care of what you need to take care of, and then moving on for the next shift. So being prepared is hugely important. So I'm skipping all the check-in and safety stuff in this particular video. Just the things I want to emphasize is that in the lab, we will be wearing masks, goggles or safety glasses, and then a shield, which we will give you, a face shield. So again, I'm not going to go over all of that right now. And actually, CDC guidelines are recommending double masking. We're not requiring that, but double masking is probably not a bad idea while we're all still waiting to get vaccinated and waiting to kind of keep this pandemic on the out. Okay, so that's enough of all of that. Let's jump right in. So I want to go through the pre-lab questions with you, some basic theory, and then I'm going to show you how to use the instrument, which is right here. And I have actually never used this instrument before, so I just kind of set it up with all the stuff that I need. So I'm going to be going through it for the first time. I don't know how much this is going to help you ahead of time. So let's go ahead and get started. Okay. Okay, hi, I'm Dr. Shane, if you don't know who I am, and those of you may have just seen me with the mask before. So all the pre-lab questions are up here. If you want to stop the video and simply copy down the 5 pre-lab questions, that's perfectly fine, you can do that. I do want to talk these through a little bit. Why are they here? And how do I have all of this organized? It's kind of just everything all at once. So what I have over here is just some basic information about electromagnetic radiation. Not going through the whole thing here. The type of electromagnetic radiation that we're talking specifically about with this lab is the visible region of the spectrum. So we are looking at, from about 400 nanometers, 10 to the minus 9th meters, and that's wavelength, up to about 700 nanometers of wavelength, the Roy G. Biv, and I think I actually did that revert, but it doesn't matter, that's up to you to piece all that together. Okay, so the first thing we want you to do, by the way, all this is in section 6.1 of your textbook, if you need a review. So this is the real basics. Remember that we view electromagnetic radiation as a wave, a sinusoidal wave. The wavelength, lowercase lambda, is the distance from peak to peak or trough to trough, and frequency is how many times the wave oscillates in a second. So frequency is given this symbol nu, and in this particular case I just arbitrarily did 3 cycles and called that 1 second of time. This is not a great example, but it makes the point. So the frequency here would be 3 cycles per second, which is, we typically don't write cycles. That's more of a physics thing than a chemistry thing. So the units here are inverse seconds, or sometimes called hertz, Hz. Again, that's more of a thing in physics. And the 2 equations, you can make 3 if you really want to, if you want to write energy in terms of wavelength rather than frequency. But anyway, the 2 of the main equations here are E equals h nu. I didn't actually put the numbers here, so this is Planck's constant. I think it's 6.6, no. I forget what it is. That's one I just never memorized. It's something 10 to the negative 34. 6.634. No, that's not right. 6.626 times 10 to the minus 34. Anyway, you can look that up. You'll probably be given that. The units on that are joules times seconds. Frequency is inverse seconds, so energy will be joules. Another equation, if you take the wavelength of light times its corresponding frequency, that is another universal constant called the speed of light, which is measured in meters per second. I think that's something like 2.998 times 10 to the 8th meters per second. But again, you can look that up. So that is a super basic overview of electromagnetic radiation. So first things I want you to do here is just pick two wavelengths in the visible region of the spectrum. Make sure they're a little different. Don't pick them within the same color. That wouldn't be useful. It doesn't really matter. So calculate the energy, calculate the frequency. Keep in mind when you pick these wavelengths from the visible spectrum, those are nanometers. So you have to convert those to meters. Calculate the energy and the frequency. To get a more standard unit for chemistry, take the joules that you get for energy and make it joules per mole by multiplying by Avogadro's number. Avogadro's number is often given the symbol capital letter N. So Avogadro's number, 6.022 times 10 to the 23rd. And then you might remember from thermodynamics last semester, we often report chemical processes into kilojoules per mole. So this is just sort of an exercise in units as well. All right. What's the next one I have here? Qualitatively determine a reasonable wavelength that's transmitted, so that you see, and a wavelength that's absorbed, so that complementary color wheel thing, for a given coordination compound. So I'm going to put my goggles on just to give a good example here. So I don't know if this is going to work in the instrument. I just grabbed a coordination compound that we had lying around, so it's yellow. Okay, and I dissolve that in water, and this is just deionized water, which we will need for the instrument. So, what will be a wavelength that's being transmitted, and then what will be a wavelength that will be absorbed for this particular coordination compound CC? Okay, so that's very basic electromagnetic radiation. Wavelengths absorbed, wavelengths transmitted, complementarity with respect to color, the old color wheel. All right, spectroscopy, quite frankly, one of my favorite topics in science. I think it's a fascinating topic. In general, spectroscopy is the study of light and how it interacts with matter. And we're going to be doing, this is visible spectroscopy. We could do ultraviolet spectroscopy. We could do infrared spectroscopy, which looks at chemical bonds. You'll do that in organic chemistry. We could look at nuclear spectroscopy by using radio waves if you've ever had an MRI. So the basic idea here with this experiment, spectroscopy is a huge field. This is not the only type of spectroscopy. So in this case, what we do is we take some light, and it's going to be of varying wavelengths, and you shine it on a sample. Okay, this is not the blank, and we actually subtract out the blank. We're going to get to that later. And the light hits the sample with an initial intensity I sub 0, or I naught. So it's initial intensity. Some of that light gets absorbed. Again, this is wavelength dependent. I'm grossly oversimplifying this. And the weight and the intensity of the light that comes through is lessened because some of it's absorbed. Okay, fine. So then we do some basic math. Is the percent transmittance for a given wavelength? It's pretty easy. It's the light that comes, the intensity of the light that comes out divided by the intensity of the light that goes in times 100% transmittance. And I gave you some totally arbitrary numbers here. These really have no physical meaning whatsoever. I just made them up. So, you'll see that there aren't even any units on here, because what I want you to do is go to your textbook. I think it's in chapter 1 or something, or you can probably just Google it. Is what is the standard unit, the SI, the System Internationale, the International System Unit for luminous intensity? And it's kind of got an interesting history, like yards and horsepower, these old outdated units of measurement. This one's actually kind of interesting, and we rarely talk about it. So assume that those units, whatever those are applied here and here. So then calculate the percent transmittance. That's pretty easy. And then you're given a formula in your handout somewhere for how do you take that from a percent transmission and turn it into an absorbance. And the formula is absorbance is minus logarithm, that's log base 10, not log base e, that would be natural logarithm if you did, of the percent transmission. So it's not a very difficult calculation. So do those two calculations, and then do the reverse. So say some instrument gives you an absorbance at a specific wavelength, not at every wavelength, of 0.213. That's a reasonable absorbance level. Calculate the percent transmission. So you have to solve the equation for percent T. Okay, I'll leave that up to you. So you have to do the inverse operation of logarithm of the logarithm. Okay. So I'll let you figure that out. It's good to kind of shore up your math skills. And so those are it for your pre-lab questions right there. So 5 pre-lab questions. Go to section 6.1. If you need to go out to the internet, like something I said here doesn't make sense, or you need to talk to your instructor during office hours, because maybe I got something wrong. Occasionally, I will do that. I don't make these videos more than once typically, and I am prone to make a mistake here and there. Okay, so what I want to do now is readjust the camera so it's kind of pointing at the instrument a little bit. And the 2 handouts you want, well, you probably already have these, are the actual handout for the use of the spectroscope. That's the actual activity that you're doing today. And I'm not going through all this, by the way. I'm not going through square planar and tetrahedral and high spin, low spin. That's going to be on you to try to piece it together with all this background. So if you have high spin, that increases that gap. So it's a more energy. How does that relate to? Okay, that's going to be on you. Square planar is. Okay, I may have gotten that backwards. I'm just kind of winging this. So that's what you're going to do with this one. The other handout you want is, it's a pretty lengthy handout, but it's good, it's detailed, is how to use this instrument. And we're not doing the whole handout here. I'm gonna jump right to the page that has all these bullet points for the operation, and then we're only using, this has 3 different experiments you can do with the instrument. We're only doing one of them, so I'm just gonna kind of fumble through this, and if it turns out this is a little bit too confusing and it's not useful to you, then we'll just figure it out when you come into lab. But the more you see the instrument, the better. Okay, so while I'm adjusting, I'm gonna put goggles on because I do have reagents here. So yeah, let's bring this up here a little bit. So I've plugged in the instrument and I've turned it on. I don't think it's really that big of a deal to let it warm up for 10 minutes, but it's definitely been warming up for 10 minutes. And I don't know, you can't really see everything. There's the screen up there. So this may not be all that useful because I don't want to make multiple videos. I don't think you're going to need me to do that. All right, so here we go. So I've got some equipment here. I've got my blank, which is just deionized water. I've got my chromophore, that's the generic word for something that absorbs radiation. It's named for color, chromo, but not everything has to have a color to absorb radiation, but we're doing visible spectroscopy. All right, and I am just gonna go through those bullet points, and then I'm gonna skip to procedure, I forget which one we're doing. I think it's procedure 5 or something like that. Yeah, because, there we go. What are we doing? We're doing this right here. All right, so bullet point number 1, prepare the solution to be studied along with a blank. I did that. Bullet point 2, put each solution in separate cuvette. All right, cuvettes are here. Now handling these, this is kind of cool. So I think it said before, and I'm going to wipe these off anyway. So the cuvettes have a handy dandy arrow. I don't know if you can see it on here. Maybe you can. And you want the light to go through this side. These other sides are slightly foggy, so I think that's it. Again, if I make a mistake, we'll just correct all this in lab. And clear the sides of the contain the blank. Okay, put each solution in a separate cuvette. That's fine. So we have 2 of these. These are pretty high-grade plastic. And don't worry about it if you handle them improperly at first, because we're going to wipe these off with cuvettes, or with Kim wipes. So just a little bit of blank. You don't need to fill these, I don't think, the whole way to the top. That's probably actually a little bit too full, because you don't want to spill anything in the instrument. That would not be good. Again, this is not the most professional video because I've never actually used this instrument before. If you've ever used an instrument like this, you probably called it a Spec200, which had 2 dials on the front, and you actually have to go through this procedure every time you measure the wave. This is much, much faster. These are much nicer instruments. Okay, so just to be on the safe side, I'm going to handle the cuvette at the top and then use a Kim wipe. These things. Don't use paper towel and don't use tissues. So I'm going to wipe off gently all sides there to get rid of fingerprints. Oils on your fingers will absorb light. They have lots of chromophores in them that will absorb light. And for the purposes here, I think that makes sense. So you want to get to this point fairly quickly. All right, so the next one, open the main chamber and place the cuvette containing the blank in the cuvette holder and make sure the clear side of the cuvette is aligned with the path of the light. So gently open this up. And again, I think I'm doing this right. Where's the arrow? And now I just got my fingerprints on it again. So I think this is the way. Again, if I get it wrong, just do it right when you come into lab. So we want to put the arrow kind of, there we go. See that okay? Okay. Close the main chamber fully. That keeps extraneous ambient light out of there. And press the 00 button. That's the blank. I think that if you read the procedure, then this makes sense. And nothing happened. Oh, you know what happened? I don't think I, there we go. Okay, I think I got it right. I may not have done that right. I think I skipped some steps. Well, you know what? For the purposes here, I think we're going to be okay if we just follow the directions. Again, I'm not really sure this video is going to help you much. And in fact, in the lab, we may... cool. Yeah, I think actually we can just do these generic bullet point directions. The specific ones, because this video is going to get too long. Yeah, I'm just going to dry lab this. So if I'm not going to get actual data here, it doesn't really matter. So you set up the instrument according to the directions. You prepare the cuvettes. You record the blank. Like I said, you have to hit this 00 button. And I don't think I did all the setup stuff correct, but that's all right. We'll do that in the lab. Then open the main chamber. So now you remove it. Now you remove the blank carefully. You can leave it open while you change this, I think. Open the main chamber. Solution. Yeah. Okay. So again, just kind of pretend here. It's kind of like when I set up, and if you had me for first semester Gen Chem, I didn't actually operate the equipment that we set up or apparatus. I just set it up and we figured it out in lab. So that's the basic idea, folks, is then you put your sample in, then you decide what are you doing. And there's three options that this instrument has. We're only going to do one of them. So you can measure the full spectrum. If you remember from the beginning of the semester, those dry lab activities that we gave you, where you had a bunch of wavelength absorbances and you made a spectrum where, you know, it went with the, whoa, you got a peak. Anyway, I don't know why I'm doing that. You got a peak and you figure out the wavelength, and that's what you can do. That's the wavelength of maximum absorption, or the analytical wavelength. So that ties into what we've already done with data. The other thing you can do is measure the absorbance at a specific wavelength. So just pick a wavelength and get the absorbance there. The one you're going to do is get the absorbance at 4 different wavelengths. So we're going to follow procedure 5 on here at various wavelengths simultaneously. So again, I didn't do this very well, but I think we'll figure it out in lab. We'll have an hour and a half, and I think it'll be just fine. So pardon me for the sort of sloppy video here, but we'll pick up where this leaves off in the lab. This just gives you a basic idea. So to reiterate, what should you do when you come into lab? When you come into lab, plug in the instrument, turn it on in the back, make sure it's operating properly, and then go through the setup procedures in the handout. or you can, I think some of your instructors may ask you to copy that down. Go through the setup procedures. Oh, by the way, when you're done, make sure you clean these out and put them back. So, prepare your blank, prepare your sample, and then follow the procedure. I don't think it'll take very long. Some of my colleagues used this instrument earlier in the semester, and it's really, really quick. So even this haphazard overview should be enough. Okay, very good. We will see you in lab.